here we go. Welcome to section 5.8, the last section in the course. Inverse trigonometric functions and integration of inverse trigonometric functions. Now, this is an introduction to something you're going to spend quite a bit of time working on in your Calc 2. But what we're going to do is we're going to be working with doing integration of functions whose antiderivatives involve inverse trigonometric functions. So they're not going to be straightforward in inverse trig. It's going to have it is going to have u substitution involved. We're going to take a look at how we can use complete and the square to make this work, and we're going to take a look at some elementary functions and some integration of those elementary functions. Okay? So it's just very straightforward integrals. So since integration and differentiation are opposite or inverse functions, we're going to take a look at the derivative rules for inverse trig, or remind ourselves of those to take and figure out how to find the rules for integration. Now, what you'll notice, or what you should remember, is that all of these over here are just the ones on the left with a negative added. So the common practice in calculus is to ignore these as possibilities. Never have an integration that ends up at arc cosine or arc cotangent or arc secant. Only use these three, and if that negative was present, just toss it in the final answer. That is, if the negative was there in the integration, then just put the negative into the argument's antiderivative. So what I mean by that is, if I ever see, and here's going to be our integration formulas we're going to be using. There are only 3 of them, so that's either good or bad, I'm not sure. Right? If I see downstairs a root of a binomial where subtraction exists in the middle, I'm going to start thinking maybe this is arcsine. Okay? If I see an integral where I have a fraction and the denominator is the binomial and it's a sum, I'm going to start thinking arctangent. And if I see an integration where the denominator is a function times a root, and the root is a binomial where the binomial is 2 things squared, I'm going to start thinking arcsecant. Now, I'll be honest with you. The first 2, seeing this pattern that exists there, these are the easier. Okay? This is the harder. Now, just because these are comparative terms, easier doesn't mean easy and harder doesn't mean hard. It just means that of these 2 things, this is the easier and this is the harder one. Okay? They're all complicated in their own ways. Okay? But these are going to be the patterns we're going to be using. These are going to be the templates that we're going to be working from for all of our problems. Right? And then we're just going to jump right into it. All right, so here's my job. I need to do an integration. Right? Now, I know that I'm in the section on inverse trig, so I know it's probably going to be inverse trig, but I want to just kind of think through the process. All right, so here is the approach that most people would do if they were handed this problem fresh, didn't know what to do. I look at it. I recognize that I have a fraction. Okay? I see a composite function, so I think maybe substitution. But if I argue that this is u, there's no du, because the du would have to require a negative 2x dx. So it would require that x dx be somewhere in there. That's not there, so it's not a substitution. Okay? Oh, well, it's a fraction, so maybe it's logarithm. Well, logarithm requires either 1 over x or u prime over u. I don't have either of those sitting here either, so it's not that. And so if it's not plain old integration, just straight up take an antiderivative, if substitution doesn't work, if logarithms don't work, now I start thinking more complicated. Is this one of the inverse trigs? I see a root downstairs. I see a binomial under that root, and I see subtraction in that binomial. that makes me think I'm looking at this one right here. My integral is a root. My integral is a fraction. The denominator is a root. The radicand, that's the fancy name for the thing under the root, the radicand, is the difference of two terms. So I can think of 9 minus x squared as that a squared minus u squared from the problem. So then a would be 3, u would be x, and then I should be able to take this just straight to the answer because I've identified the a, the u, all the pieces and parts are needed there. Okay? Because if u is x, then the du is the dx for my numerator there. And so now I can just say, okay, well then this is the integral of du over the root of a squared minus u squared. That's equal to, I'm going to copy it down from the formula, arc sine of u over a plus c. So now since all of the pieces and parts match up, I can then say that my answer, or the value of this integral, is going to be the arc sine of x over 3 plus c. So I stared at it for a second. I said, this looks like arc sine. If it is arc sine, then the radicand better be a squared minus u squared. So I identified a, identified u, I figured out my differential du. I made sure that all the pieces and parts that I needed matched everything over there that needed to match. Okay? I'm comparing the dx over the root of 9 minus x squared to the du over the root of a squared minus u squared. So a could be 3, u can be x, du can be dx, and everything matches. Plug it in, grind it out, and I've got my answer sitting right there. Now, all the problems aren't going to be quite that straightforward. Look at this one. What do you see? Okay, well, I'm given integration. It's not plain old integration because fraction. Numerator is not the derivative of the denominator, so it's not logarithm. I don't see composition in any way that would work, so I don't think this is u substitution. So maybe I'm thinking arc trig. My denominator is a binomial, and it's a sum. So I'm no longer looking at arc sine. Now I'm looking at u arctangent. I'm looking at number 2 there. Okay? So what I'm going to do is I'm going to copy that formula down and see if I can make all the pieces and parts match. The formula says du over a squared plus u squared is going to be equal to 1 over a arctangent u over a plus c. So now what I need to do is I need to compare what I'm supposed to be seeing for this to be arctangent to what I actually am seeing. Right? Well, if this is arctangent, then 1 plus 9x squared needs to be a squared plus u squared, which would mean that a would have to be 1 and u would have to be 3x. And I'm going to highlight that because that's the mistake that people will make. They'll forget that that entire term, 9x squared, is equal to u squared. And they'll just do the x squared is the u squared, and they'll get that u is 9x instead of 3x. So be careful with that one. Okay. Now, if u is 3x, then what's the differential du? Well, the differential du would be 3dx. 3dx, but I've got 12dx. So how do I make 12dx be 3dx? Well, 12 is just 4 times 3. And so I'll just take that 4 and move that part of the coefficient out in front so everything matches. So then I've modified my integral to be 4 times 3dx over 1 squared plus 3x squared. And now all the pieces and parts match perfectly with what they're supposed to match with. And I can just say this then becomes 4. And where'd that 4 come from? Well, there's the 4 out in front. Times 1 over a, and we decided that a was 1, arctangent u over a, and we said that u was 3x over a, which is 1, plus c. And then the last thing I'll do is I'll clean that up a little bit. For arctangent 3x plus c. Now I know there's at least one person out there who's watching this video who's going, can't I do this? And I will tell you that yes, you can, because the tan to the negative 1 notation is acceptable for arctangent. I prefer not to, for the same reason why I don't like using y prime, why I prefer dy dx. And it's not about accuracy, it's not about any sort of correctness, it's just a matter of there's been too many situations where that negative 1 has become lost, and it's suddenly become 1 over tangent, or maybe just lost altogether and just become tangent. And so I prefer to keep the arc on the front. I screw it up less. I make less mistakes. I know it's extra writing, so it goes against my lazy principle, but it is something that I do because I've just made the mistake too many times, and I don't want to make the mistake again. Okay? All right, let's try this one. I have the integral of t over the square root of 1 minus t to the 4th dt. Okay. It's not plain old integration because it's not one of those integration rules I memorized. It is a fraction, and downstairs is composition. It's not logarithm because it's not u prime over u, because that means u would be the whole root. Maybe it's substitution. Maybe I need to do substitution. Okay, so I'm seeing downstairs, here's the inside of the composition, so let's try that and see what happens. 1 minus t to the 4th. Then the differential du would be negative 4 t cubed dt. But that doesn't work because, oops, wrong one. I wanted the highlighter. You think by the now I'd have figured this out. Okay? This is not the t cubed part of that. I mean, I can deal with the coefficient. That's not an issue. We figured out how to deal with coefficients. But I've got t, and it needs to be t cubed, and I can't just chuck in some extra t's. I know that earlier in our substitution section we factored out if we had too many, but adding some in if I don't have enough, I can't do that. So it's not plain old substitution. Well, if it's not plain old substitution, then I need something more powerful. Maybe it's arc trig. So I'm going to go back up here and look at my possibilities. Downstairs is a root, and it's only a root. So the only possibility is maybe it's this guy somehow. So I'm going to copy that formula down and see if I can figure out how to make it work. I'm thinking it's maybe something to do with this guy. A squared minus u squared. And this is equal to, what was that equal to? Was it arc sine u over a? There we go, arc sine u over a. Wait, I'm here. Okay. So, if this is going to be arc sine, then somehow t dt needs to match up with u du, and 1 minus t to the 4th needs to match up with a squared minus u squared. So I'm going to start trying to make that work. If 1 minus t to the 4th is going to be the a squared minus u squared part, then a squared is 1, or a is 1, and t to the 4th is equal to u squared, which means that t squared is u. Are you with me there? And if t squared is u, then 2t t dt would be our du, and I just saw what I needed to see. Do you see the t dt for the du? I'm not worried about the 2. I can always fix that. I can get then that t dt is 1/2 du, and I've got everything I need to have to make this work. So now I can do the substitutions, if you will, or I can just go straight to the answer. The only thing I got to worry about is how does this show up in the end? Now, there are some people who argue that you should rewrite this integral using all of these substitutions that we just did so that you can see how things happened. Right? And so if I make those substitutions, now I have the integral of 1/2 du over the square root of a squared minus u squared. And so the only difference between this one and this one is simply a coefficient. And so then this will just be 1/2 arcsine u over a plus c. Right? So then putting it all together, we're going to get 1/2 arcsine. U was t squared. A was 1 plus c, or 1/2 arcsine t squared plus c. All right, I'm going to stop this video here. It's been about 17 minutes. We'll come back and do some more examples. See you for part 2.